Welcome everyone, and thank you for attending this webinar on powder caking, understanding different caking behaviors and the influence of humidity cycling. Our presenter is Dr. Guy Stimpson. My name is Jeff Canvin, and I'll be the moderator for this webinar. Before we begin, we want to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you may use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We'll try to answer these during the webcast, but if we run out of time, they'll be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available today and will be emailed to you once the session has concluded. I'm pleased to introduce today's speaker, Dr. Guy Stimpson. Guy is currently an application scientist with Freeman Technology, a micromeritics company based in the United Kingdom. Guy received a bachelor's degree in astrophysics from Aberystwyth University. He then went on to study experimental quantum physics at Warwick University, culminating in a PhD. Guy currently works closely with researchers and engineers from across industry to develop and implement advanced methodologies for testing of powder flow systems. Guy, it is an honor for me to introduce you, and we are so glad you could be here to share your insights on powder caking, understanding different caking behaviors, and the influence of humidity cycling.
Hello, and welcome to another instalment of the Micromeritics webinar series. My name's Guy Stimpson, and I'm an application scientist at Freeman Technology, a micromeritics company. Today, I'm going to talk to you about powder caking and how we can understand different caking behaviours and the influence of humidity cycling. Please feel free to add any questions during the webinar, and we'll address some of those in a session at the end. Firstly, it's important that we define what exactly is meant by powder caking. Although it is an ever-present concern across many different powder handling environments and different industries, caking can have a variety of implications dependent on the particular usage for which a given powder is intended. In general, though, caking can be defined as a powder's propensity to form dense lumps or masses which can interfere with the processability of that powder. This densification of the material can be due to the uptake of moisture from the atmosphere, consolidation of the powder through deaeration, or chemical reactions operating between particles. But perhaps caking is a misnomer. Does the powder indeed form a cake-like structure with layers of different strength and texture? Or is the densification of the material homogeneous throughout the powder bed? Often it's assumed that caking is a sample-wide process, which simply results in the whole portion of powder being rendered unsuitable for use. But is it possible that different regions within the sample may respond differently? Or could it be possible that some powder could be returned to its original usefulness by further processing? Traditional forms of powder flow measurement are unable to investigate this question, as they are unable to sample the powder at differing points within the powder bed. By contrast, powder rheology offers the facility to subsample the powder bed and provide an in-situ understanding of caking behaviours. Before we dig into the causes and effects of caking, let's take a moment to understand why caking presents such a problem to industry. Firstly, caked powders which cannot subsequently be used must simply be wasted, which is undesirable in itself. However, perhaps worse than this is the prospect of blockages occurring after the powder has entered the process. This can lead to downtime and production loss which, depending on the process itself, can be very lengthy if the blockage is difficult to clear. In some cases, it's even possible for caked powder to cause damage to the process equipment, which can have devastating consequences for obvious reasons. With this in mind then, understanding not only when caking happens, but also why and in what way it happens, as well as its impact on process, it is of critical importance in many industries. Now, let's look at the mechanisms by which caking can occur. Chief among these is the interaction between the powder and moisture, usually in the form of humidity. Whilst moisture is not the only driver of caking, it is perhaps the most prevalent and difficult to combat. Predominantly, moisture-induced caking takes the form of deliquescence at the particle scale. Moisture is absorbed and adsorbed from the atmosphere, which can lead to expansion and softening of the particle, which in turn allows for the deformation of the surface. At this point, liquid and solid bridging can lead to mechanical bonding between particles, and chemical reactions can lead to alteration of the particle properties. Depending on the exact nature of this deliquescent behaviour, this process may be irreversible, or it may be partially or wholly reversible. Whilst it's easy to see how these interactions with moisture can modify particle properties and lead to increased bond strength between particles, it's not solely responsible for caking. We also need to consider the effects of the reorganization or rearrangement of the particles due to external drivers. Consolidation can occur through vibrations allowing the particles to slip into a more organized state, which is accompanied by deaeration of the powder as space taken up by air is replaced by particles. And we may observe active compression of the powder by some external force. This could be applied deliberately or, more often than not, simply by the mass of powder acting upon the layers of powder below, or containers of powder being stacked on top of each other. So, what's the realistic picture then? In reality, it's unusual that we'd have a single caking mechanism responsible for all the changes we observe through the powder bed. Much more likely is that we see a combination of these factors, all acting together to alter the behaviour of our powder. If we take a particular sample of powder, we'll observe atmospheric gases, particularly those containing moisture, entering the powder bed through exposed surfaces and then circulating through the bed, slowly diffusing depending on the particular geometry of the system. Gravity will also apply some force, crushing the lower layers of material due to the weight of the powder above, and any vibrations will exacerbate this process by making it easier for particles to slip down. Finally, we may observe chemical reactions fundamentally altering the properties of the particles. These processes all add together to leave us with a powder which may be markedly different in behaviour to the one we started with, and of course, increased exposure to these forces over time can increase the severity of their effects. Now seems like a good time to discuss why it is that powder rheometry is the tool of choice when investigating powder caking. Traditional methods of powder testing, such as angle of repose, Hall flow, and tap density, are unable to test a heavily caked sample, as they each require the entire sample to be disturbed during testing and/or to flow reliably. A caked bed will be fundamentally altered if it is disturbed, and will often not flow well enough to be tested by these methods, or it will not flow at all. One alternative testing method which has been used in the past is the shear cell test. This long-established method is designed to measure the propensity of a given powder to flow against itself, and it provides a detailed mathematical understanding of how powders behave under high-stress flow conditions. It is a powerful tool which has produced a number of successful results in the past. However, the shear cell is only able to test the very top of the powder bed, as it interacts with a complete cross-section of the sample simultaneously. The process by which the test takes place results in severe modification of the rest of the powder bed, and so it's not possible to understand what changes have taken place deeper into the powder. Contrastingly, powder rheology is able to measure multiple points throughout the powder bed, providing a detailed picture of the caking behaviour throughout the sample without disturbing the as yet untested regions. This leads to a more reliable and detailed result than is possible with any of the competing methodologies. Powder rheology allows us to analyse the flowability of powders not only at a single point, but throughout the sample, by passing a specifically shaped impeller or blade through the entirety of a given sample. As the blade passes through, it measures the resistance of the powder to its passage by detecting both vertical and torque forces imparted by the particles. These are combined as a function of height or depth of powder to produce a flow energy measurement, which gives a description of the powder's propensity to flow under confined conditions. In an uncaked sample, we would expect to find lower stresses, i.e. a looser packing state, towards the top of the sample vessel. Therefore, comparatively low force and torque would be measured here. As the blade's height above the base of the vessel decreases, though, we would expect the packing state of the particles to become more efficient, as gravity and mass cause the compaction of the powder. This would be expected to lead to higher stresses, and therefore increasing torque and force measurement, coming to a maximum at the base of the vessel. This tends to be a roughly exponential increase and describes a fairly smooth curve. For the experiments performed in this study, samples were conditioned by using the blade to break up any loose agglomerates or air pockets and to leave the powders in a loose, homogeneous packing state. This ensures that testing is reliable and repeatable, and that any operator influence is minimized. The samples are then stored in a controlled atmosphere, with the relative humidity set by the use of a desiccator and salt solutions which provide a stable, reliable level of humidity. Gravity will cause some consolidation of the powders, but for these particular experiments, no mass was applied to the samples other than their own weight. Multiple identical samples were prepared and stored, with samples tested one by one at a fixed time interval. In this case, there was 1 day in between each test. When the samples are ready to be tested, a single flow energy test is performed, and the combined force and torque generated by the blade's passage can be examined. First results are from sorbitol, which demonstrates typical homogeneous caking. The dotted line shows the flow energy of the powder for an uncaked sample. Here we can see that, as expected, the energy increases simplistically with descending height into the vessel. The subsequent lines, in increasingly pale blue, show the progression of the samples in time. As we can see, increasing time corresponds directly with increasing flow energy. This indicates that as time goes on, the flowability of the powder decreases. We refer to this mode of caking as homogeneous because the change in energy throughout the powder bed is fairly even. We see no layering and no change in the texture of the powder as we go deeper into the sample. By contrast, the results from skim milk powder show a very different result, which we describe as inhomogeneous caking. Here we see a number of interesting features. On the first day, there's an increase in flow energy only at the surface of the sample, which suggests the formation of a weak crust, the first evidence of any kind of layering effect. Secondly, we notice that with time, the crust progresses downwards through the powder bed, leaving a trail of caked powder behind it. Though the crust itself has clearly the highest flow energy, and therefore the most reduced flowability, the formally crusted region is also significantly less flowable, leading to the majority of the sample having been affected by the end of the test. Lastly, we also see that the regions of the sample below the crust are almost entirely unaffected by the caking. This is an important result because although in the case of homogeneous caking we may have had to dispose of the entire sample, in this inhomogeneous case we may be able to salvage some of the material and use it in our process. In this last sample we see a hybrid caking effect, where both homogeneous and inhomogeneous modes are contributing to the changes through the sample. The lower regions of the bed seem to increase in energy in a similar fashion to the sorbitol we saw at the beginning of these results, whilst the upper regions behave differently again. Here we see the formation of a crust, but this low flowability, high flow energy region gets both thicker and stronger as time progresses, and unlike the skim milk powder, the crust remains in place and does not migrate. Here then we have three distinct caking modes, all with differing implications. Both homogeneous and hybrid caking modes are likely to result in large amounts of material wastage, whilst the inhomogeneous mode may permit us to preserve at least some small proportion of usable powder. Similarly, we see different crust behaviours, which we will look into in more detail shortly. Difference in the behaviours of the crust may be linked to the particular relative humidity set. In this case of milk powder at 75% relative humidity, we can see that, as previously, we have a surface crust which then migrates deeper into the sample whilst leaving a partially crusted region behind. At 53% humidity though, the surface crust is largely maintained, although its thickness does seem to increase. Importantly though, in both cases we see the preservation of the region below the crust, across the timescale of the experiment at least. We can also see that the overall depth of the crust, whilst a little thicker at 75% RH, evolves in a similar way for both samples. In both cases though, the crust thickness will of course determine what proportion of powder remains available for use once the crusted region is discarded. It could also be used to predict the thickness further into the future, giving an idea of viable storage times for larger samples of powder. We can also assess how strong the crust is when considered as a whole. By dividing the energy of the crust by its depth, we can decide whether or not the crust is hardening or if it is merely a thicker, weaker crust. Evidently, the higher humidity results in a much stronger and faster response in terms of the ultimate strength of the crust, whilst in the drier environment we see a slower progression. Importantly though, the more moist environment may result in a cake which reaches a plateau in crust strength and subsequently ceases to develop. By contrast, the drier environment sees a crust which is not only continuing to develop, but also to strengthen with gathering speed. A longer-term experiment would need to be performed in order to understand how long this increase would go on for, but it's clear that even in a drier environment, long-term storage could be highly detrimental to this powder's flowability. So far, we've seen that powder caking can depend on the powder itself and on the environmental conditions under which the powder is stored. However, the evolution of the caking is also worth considering. Here we see a case where the particular caking mode of the powder changes with increased storage time. Whilst initially we see a fairly ordinary, homogeneous behaviour, by the second or third day a crust has begun to form which then seems to influence the development of the caking lower down in the sample. Once this crust has formed, we can see that near the surface the energy is increasing much more strongly with time than it is in the lower layers. There is still an increase in the lower level energy, but much less pronounced. It may be that the surface crust is limiting the amount of atmospheric gas and the moisture it holds which can penetrate into the bulk of the powder. So far we've seen the effect that storing our powders in a humid environment can have on their flowability. However, in many of the examples we see that the entire sample may have had to be discarded due to the effect of the caking. This is obviously undesirable to say the least. So is there any other option? Perhaps we can recondition the powder by storing it for a time in a much drier environment. If this was the case, then caking would be a reversible process, which would undoubtedly be beneficial. To investigate this, we stored samples at 75% relative humidity for 3 days, and then transferred them to a drier environment at 33% relative humidity for an equal length of time. What we see is that again, different powders display different responses to this drying process, which once more has implications for whether powder can still be used in process or whether it must be discarded. Here, the initial caking is shown by the dark blue curve, whilst the dried sample is indicated by the orange curve. Clearly, there has been a change in the caking mode, but the results are probably not what most operators would hope for. Caking has increased throughout the powder bed, with both the surface and subsurface increasing in energy. Prior to the drying, the sample may have been usable as, although there was some caking in evidence, it was mostly fairly weak and homogeneous throughout the sample. After drying though, there is now a strong, thick crust, and the lower levels of the sample have also become less flowable. Most likely then, the entire sample could not be used and would need to be discarded. Here we see a much more favourable response. Though during the caking phase a strong, thick crust had developed, the drying process seems to have largely mitigated this effect and left us with a much weaker caking profile. The powder bed does seem to have maintained some added strength, but on the whole the impact on the sample has been greatly reduced, and depending on the process for which this material is intended, the powder may still be suitable for use, saving on wastage and reducing the chances of downtime. Lastly then, we see the process of homogenization, where a sample which initially developed a strong, progressive crust was dried out, resulting in a much more even distribution of the caked region. The implications of this could be different depending on the particular details of the process for which this powder is intended. On the one hand, after the initial caking, the lower half of the sample was almost completely unaffected, so may have been salvageable, whereas the dried sample experienced an increase in the flow energy throughout the bed. On the other hand though, it may be that in reducing the crust strength and distributing the caking throughout the entire sample, the flow energy may now be low enough to maintain a reasonable level of processability. In either case, the particular result depends heavily on the specifics of our process and how much of a decrease in flowability we're prepared to accept in order to prevent wastage. In conclusion then, we have seen that caking is not a simplistic process, and it depends on a number of factors. Here we saw that the materials themselves, the time for which they're stored, and the humidity under which they're stored all play a part in determining not only the extent of the caking, but also the particular manner in which the caking occurs. However, we should also remember that temperature, applied mass and other storage parameters could have a further effect on the mode and the severity of caking, although we didn't address those here. We've also seen that caking may or may not be homogeneous, with different caking modes being exhibited depending on the material and environmental conditions mentioned above. This detailed, bed-wide analysis allows us to understand more than just the degree of caking, but also how different points throughout the powder bed are affected, which allows us to make more informed decisions regarding preservation or disposal of our caked powders. Aside from that, we've also seen how the layered picture of a traditional cake may not always be too far from the truth, and that different flowabilities and textures of powder can be found, dependent on the particular caking mode. How this knowledge will translate into our processes depends on the specifics of the processes themselves, but undoubtedly this can be vital information when attempting to reduce both wastage and process downtime. We've also seen that drying powders may be a route to reversible caking, with the flow energy across part or all of the powder bed being reduced in some cases. Dependent on the system, this may lead to some powder being recoverable for reuse and wastage being reduced. However, we also need to be aware that drying may not always improve the flowability of a caked powder, and can even lead to the opposite result, with dried powders becoming less.
Thank you, Guy. I'm opening the chat for everyone's questions now, and we already have a few. Guy, are you able to see the effects of other changes in powder flow over time, such as the effect of temperature?
Hi, thanks, Jeff, and thanks everybody for coming. Yeah, absolutely. So really anything that is going to impact the ability of a powder to flow is going to affect the sorts of results we saw there today. So for example, if there was some sort of long-term effect of temperature change, such as sort of deformation of the particles or again, sort of any interaction with moisture due to that temperature change, then that would have the same kind of effect on the powder flow itself, and we'd see the same kind of results. So really what the FT4 does, it doesn't measure the particular parameters or the particular properties of the powder, it measures the effect that those properties have. So anything like temperature or whatever is going to have that kind of result.
Thank you. You showed in a very nice and comprehensive way basically this behavior of homogeneous versus inhomogeneous versus even hybrid caking and the effects there. Can we detect agglomeration in samples in a similar way?
Yeah, absolutely. So if we were to look sort of down through the powder bed, agglomerates would essentially provide a greater resistance to the passage of the blade just through their increased mass. So where we see sort of, significant agglomerates within the powder, that manifests itself as a sort of short-term increase in that flow energy. So if you can consider a sort of perfect powder, that would have that very smooth increase in energy that we saw in some of the earlier slides. Whereas if we were to see agglomerations in there, we would see sort of peaks in that kind of data as well. So those agglomerates show up as really as noise within that data.
Thank you. With respect to the types of powders, are there any restrictions on the types of powders you can test in this device in this way?
No, not really. So when we describe powder, we really mean anything from the nanoscale right up to sort of things a centimeter or so in diameter. So really well beyond the world of sort of powders and right up to pellets and things like that. So the particle size doesn't really affect us. In fact, one of the reasons the EFT4 was built is because some of the traditional testing methods, such as sort of angle of repose and flow through an orifice, these are restricted. You can have a lot of powders that won't flow in those conditions. But we don't have such a restriction with the FT4. We don't get those no-flow environments.
The focus today was really on caked materials, but what kind of information can we get with powder rheology with respect to uncaked powders?
Yeah, okay. So really powder rheology, sort of the initial intention of that is to focus on sort of uncaked powders. So we can look at anything from, the sort of flowability that we've described here, which is describing flowability in sort of confined conditions. We can also look at sort of free-flowing powders, in pouring and filling operations. We can investigate the cohesiveness of powders. Then we also have things like the bulk characteristics of powders, so the compressibility and the permeability of powders. And lastly, we also have the shear cell capability on the FT4 as well. So really what we're able to do is analyze powders throughout the full range of their environmental conditions. So whether it's cake powder, whether it's dynamic moving powder in some kind of process, whether it's static powder in a hopper, we're really able to look at that full spectrum of powder behavior.
This is a little bit beyond some of the material you presented this morning, but do you have any type of recommendation for, what could possibly be added to mitigate this issue of caking?
So, I mean, there's kind of not really for me to say because, we're an instrumentation manufacturer. However, there are a range of different sort of anti-caking materials out there. But I think what this really does is first allows you to understand, sort of how severe your caking problem is. And then if you can find something like one of these anti-caking agents, you can then assess how successful they are in preventing that caking. So we don't provide any method of preventing the caking itself, but we can demonstrate how effective that caking is and what sort of steps that you can take to prevent caking in your powders.
So, you showed very nicely multiple tests on multiple samples that have been exposed to moisture. How much material would typically be required if you wanted to complete one analysis with the FT4?
So it varies depending on a number of factors. So if we have larger particles, we tend to need a larger sample size. But for taking sort of 250 micron or smaller particles as an example, a single test will be between 10 milliliters and 25 milliliters of powder, depending on the kind of test we're doing. It's 25 milliliters for the sort of test that we did here. So if you were going to look at 5 days, then you're talking sort of 125 milliliters in total for that. You may need a little excess because we sort of chip off some excess at the beginning of the test, but it's around that 25 milliliters per test sample size.
So, this next question that was submitted, or really two questions, how is powder consolidation study for this type of device, and how do you define the consolidation forces that are applied?
Yeah. So we have a similar, slightly different test for consolidation. So typically people have looked at tap density when considering consolidated powders. Unfortunately, this is subject to a couple of issues. So firstly, the preparation of samples has a strong influence on their initial state. So the amount of consolidation you'll apply during your tapping will change in those powders. We actually condition the powders first so that we always get a nice consistent amount of consolidation. We then run something very, very similar to this, i.e. a flow energy test. So we're able to define what the effect on flow energy is due to any consolidation you've applied. Now this works in concert with sort of any standard tapping device, really, any tapping volumeter or auto tapper, but it's really the same kind of test that you've seen here, this blade traveling through the powder. Now, we can have a look at this just in a simple, well, how's it affected the average flow energy of that sample, or we can look at in this same sort of height-dependent way that we've seen in the caking test here. Now, what we don't do is quantify specifically the forces that are taking place during that consolidation process, but we are quantifying the effect of that consolidation, and we really do that in terms of the flow energy.
Another question that was submitted, really a bit challenging. How do you study the effect of temperature and humidity in combination with the effect of weight?
Yeah, okay. So generally we would do this off the instrument. So for temperature, we would look at an oven, excuse me, and for humidity, we look at, for example, a desiccator. So we try to keep this kind of testing off the instrument due to not wanting to damage the instrument and whatnot, but actually it gives you much better control of your environmental conditions if you're off instrument there. So really a case of placing your sample, as we've done here, but inside that controlled environment where you have your temperature and your humidity control, and then returning those samples to the instrument for the testing. The testing's pretty quick, and it's also very modifiable. So we can do things like reducing the number of, well, in fact, removing for this sort of test, the conditioning steps and things like that, so that we can get that data very, very quickly once the sample's been removed from its environment. But really having that off-instrument control of your environmental conditions is really a more successful way of testing than trying to do it on instrument. So it's just a simple case: place your sample in your controlled environment and then return it to the FT4 for the testing.
Early in your slide deck, you had mentioned the different effects or the different factors that can impact caking. In the work you showed this morning, is there a specific case that could be related back to chemical reaction, or do you have a specific case study that shows, how chemical reaction shows up with caking?
Unfortunately not, because this kind of effect is incredibly powder specific, sample specific. So like I said sort of a little earlier on, we really look at the effect that these various factors have. Now, if you're able to understand, for example, each of these different factors individually, that would be fantastic. But that's not really part of the scope of powder rheometry. And I think that's really because it's such a complicated thing to add those various things together. I guess that kind of experiment would be possible, but I think it would need really quite a sort of an in-depth investigation that would be beyond the scope of the FT4.
In the work you've done, is there a way to identify caking on the bottom of a container simply from its own mass?
So I guess this means if you're using a kind of, if you've got some large container that is sort of pre-caked and you want to investigate that, I mean, depending on how you remove the sample from that caking, then it would be perfectly possible to test that on FT4, yeah. However, you're going to have things like the effect of removing that sample from that container is likely to have some impact on the flowability of that sort of that sample that you've removed. So whilst it's absolutely possible, I think performing the caking sort of in situ in the sample vessel is going to give you a truer representation of what's happening. By removing that sample from an active container, there's always the risk of that disturbance.
You showed really nicely the effect of moisture and then drying of materials. This next question is a bit more related to storage. Do you have any experience or seen materials where they've been stored in a pressurized environment with dry gas, basically to reduce flow problems? Have you seen this type of storage and then basically flow properties of those materials?
So I personally have not. I have not done anything with pressurized powders, but we certainly have customers out there who are exposing their powders to these sorts of conditions. And again, really, the method of testing would be the same there. So you sort of take a powder you haven't treated. I would always do that first to understand how that powder behaves without these kind of environmental constraints, and then directly test the treated powder. Now, depending on the nature of that treatment, it can be that you can test in situ with the FT4, but most likely I think it is that you'd have to remove that material and test it on the FT4 outside. But again, I think those pressurized environments, really you're just applying some kind of condition to the powder, and then you'd be able to test it. So I'd expect to see kind of similar results, or at least results that could be interpreted in a similar fashion.
So for materials that are stored during high humidity months of the year, where caking is a problem, what would be some strategies for testing those materials? And then likewise, are there good strategies for then adding anti-caking additives or basically testing different types of packaging materials? What would be your strategies for testing for these kind of problems?
Okay, yeah. So I think in this case, what we do is really a sort of something similar to what we've done here, but really spread out over a longer length of time. So if we're talking about, say, looking at it in the summer and in the winter, if the summer is where the problematic caking occurs, again, what I would do is make sure I'm testing in the winter as well. But then what I'd be looking to do, either you need to be replicating these changes in humidity artificially, as we've done here, or I think, personally, my feeling would be the best way would be to do it with the realistic conditions. So taking some of that powder that you've added your anti-caking agents to, storing them in the way that you normally would, and then perhaps at the height of that caking or the height of that season, bringing both the sort of untreated powder and the treated powder to FT4. So really, I would expect a very, very similar set of results again for that. But obviously, you've got a time constraint in there as well, so maybe we'd be looking over the year. But for me, what I'd be ensuring that I did is, let's say we're talking over a 6-month period, I'd be taking subsamples of this, perhaps every 2 weeks or every month through that period, so that you can identify when it is exactly that the caking reaches its peak. You could also do things like continue sampling for a little bit after, where you expect that sort of max maximum caking period to be. So you might see that actually if you leave those samples for a few weeks, maybe some of them improve, maybe it gets a little bit worse. So something like the sort of humidity cycling that we saw at the end there. So I think, really to represent the behavior most accurately, I'd be wanting to do it over that time, but you could do it in a sort of shorter period by artificially manipulating the conditions as well.
If we wanted to differentiate between caking and agglomeration, is there a strategy that we can use to make that differentiation?
Yeah, I mean, I guess what agglomeration really is caking over short scales, right? So short range caking. So fundamentally, there is kind of no difference. But then, of course, when we actually see this in the sample, we have kind of locally caked regions, i.e. the agglomerates, and then sort of widespread caking, which is what we see in here. So yeah, I would expect to see differences. Almost, so if you think back to where we had the sort of crusting behavior, we saw these kinds of strong peaks sticking out. Sort of discrete versions of that spread out over the powder sample might be what we'd expect from agglomeration, whereas the caking we would see in this kind of more defined zones or in the homogeneous case. So yes, I would expect to be able to identify the differences between the two, but fundamentally they're the same. So they're not going to show you anything wildly different. There's going to have to be some point where you're going to have to say, well, this is what we're going to categorize as agglomeration, and this is what we're going to categorize as caking, because really they're the same thing. It's just kind of a personal choice almost to define which you mean by the two.
You really demonstrated nicely the effect of moisture on these different materials. Have you seen or have you used other gases to basically induce caking or lead to caking in materials?
So generally what we focus on is just the sort of the effect of the relatively natural environment, but there's no reason that can't be done. So with the FT4, as it comes out of the box, you can test with oxygen and you can test with nitrogen, the various range of tests we can do with that. However, I think if you wanted to use something like argon or some other gas or anything like that, really that's going to be coming down to how you can store your powders. So again, if you're using a desiccator to create your environment, you're going to need to be able to do that with that particular gas. Obviously, then you're going to have to think about preventing that gas from escaping, etc. But there's no fundamental reason why you shouldn't be able to do those tests. And again, I'd expect the same kind of results to result from that kind of testing.
On your testing with the FT4, is there a quantitative way to correlate the change in force from the rheometer to changes in powder flow properties?
So the flow energies that we normally measure are comprised of force and torque. So we measure those two different components independently, and then we combine them to get our flow energy. So you'd be able to extract the force as a single thing. So we can also apply force in any way we want to, really, using the FT4. So for example, if you wanted to say, well, yes, we just want to see the effects of applied force, you'd be able to sort of apply that force on the FT4 and then take a very similar measurement as we've seen today. So I think if you've got a sample which you have applied force to and you've applied a modified environment, it would be very difficult to extricate the two results. But if you can perform two tests, one where you're just applying the force and looking at the flow energy, and another test where you're looking at the effects of moisture, then you'd be able to identify the effects of those two independent factors there.
Thank you. Early in your slide deck, you mentioned some of the testing, such as shear cell. Can you comment, just some general comments on comparing data, specifically with respect to flow function between a shear cell and the FT4?
Yeah, so Obviously, we have a shear cell on the FT4 itself. It uses a slightly different geometry to other shear cells, but really the results are sort of largely comparable, maybe with some kind of offset, something like that. A lot of people will spend a lot of time arguing about which is kind of better. However, what is important here is the shear cell is really designed to look at a specific set of powders in a specific set of conditions. So shear cells work particularly well with sort of slightly cohesive powders or more cohesive powders, and it likes to work with them at high stress. Where we see powders outside those kind of regimes, so more free-flowing powders or powders under lower stresses or fluidized powders, that's really what the FT4 was designed for. So I would actually encourage people not to try and develop correlations between shear cell results and the sort of dynamic results that we get on FT4, because the shear cell model really does start to break down under the sort of under those lower stress regions or under those more those less free flowing regions, and the dynamic testing on the FT4 really starts to pick up in those cases. So our experience is that it's really best to be using the shear cell and the dynamic tests together to complement each other, rather than trying to use one to do the job of the other, because they don't really match up so well. There are some cases where, you know, powders which behave in a certain way at lower stress will also behave that similar way in the shear cell, but I think you don't really know that until you've looked with both methodologies. So I would really encourage people not really to try and link the two. It tends to not work out very well.
For these caked materials, can you comment on what could be some causes of random lumps of caked powder versus full layers of caked material?
I mean, really, this would be speculation on my part. I guess if you have some uneven consolidation of your powder or any kind of pre-existing agglomerations or sort of loose associations of powder, then that's really going to disrupt things like the diffusion of the atmospheric gases, and also if you're using applied force, it's going to affect the distribution of that force. So I think it's difficult to separate sort of, you know, random effects. But one of the reasons that we're trying to do this over a large sample area is so that any kind of random effects are averaged out, really. So I think, actually, another point I should raise is we have the conditioning step, which should really be mitigating any of these kinds of differences in packing or differences in the sort of powder condition through the bed. So I would really hope that we shouldn't really have any random effects. I think if you did have those random effects, it's going to be quite difficult to remove that. But then, you know, having said that, if you've got a number of samples of powder and you're sampling over a few days, then again, I would expect those kind of random effects to be mitigated by that.
A really practical questions concerning using the FT4 for these types of studies. Your work, very nicely, you were able to demonstrate how this effect of caking over days. How long does it take to conduct a typical test on the FT4? And then can you apply this type of testing to materials that cake rapidly, perhaps within a few hours rather than days?
Absolutely, yeah. So one of these tests, in fact, if you just take one of the sort of the down traverses of the FT4 that we've used for these tests here, you're talking a few seconds for that actual for the actual execution of that. Obviously, there's a little bit of moving your sample around in that time and whatnot. But yeah, absolutely. If you're seeing effects in hours, I would absolutely be able to. I would actually absolutely expect to be able to see that with FT4. We have some customers that are adding, you know, sort of liquid additives to their powders, and you can see reactions, you know, on the scale of sort of 10 minutes, 20 minutes, and we can see the effect of that exactly in the same way as we see here.
Uh, with respect to morphology, particularly particle size, are there any size restrictions on what can be analyzed with the FT4? Particularly, someone's inquiring about size ranges from about 0.5 to 5 millimeters.
Absolutely not. That's absolutely fine. So we have a range of sample vessels and blade combinations, and that really allows us to do anything up to, I mean, our limit's going to be somewhere around 10 to 15 millimeters, depending on what we do. But 5 millimeters is no problem at all.
It's really similar type of question, and maybe extending upon it. When you look at particle size and morphology of pharmaceutical powders, what type of influence do these have on caking behavior with respect to varying humidity?
Yeah, okay. So I would say I mean, it's kind of a two-pronged question, really. So I'm going to go with particle size first. So I think the biggest contributor to caking is likely to be, and I must point out there's a little bit of speculation here, but I would absolutely expect the contribution from fine particles to be extremely important in caking. If we consider, if we take the most simple form, a sort of spherical particle, and let's say we have something, I don't know, 100 microns in diameter. When these particles are stacked together, we're going to have a lot of empty space in there. And that empty space is surface area of particles that isn't in contact with other particles. Now, when we start to throw fine particles into that, those fine particles tend to fill up those gaps, those spaces in between the larger particles. And now that sort of empty surface area has now become contact area. Where we have contact area, we have the potential for that caking to increase. So I would expect particle size distribution rather than particle size itself to have a significant effect. As well, though, I think, when you increase the particle size, you decrease the contact area as well. So particle size itself would have an effect too. Again, with particle shape, it's going to be all about affecting those surface contacts, those contact surface area. So I think where you take a perfectly spherical particle, that contact area is going to be fairly minimal. As we start to move to more irregular particles or particles with more flat surface area, you're only going to increase that contact patch, and therefore that's going to increase the chances not only of chemical reactions, but liquid and solid bridging is likely to increase as well. So yeah, I think both particle size and particle shape are going to have a significant effect on the powder's propensity to cake.
Guy, do you have recommendations for how you would use the FT4 specifically for additive manufacturing powder printing and with respect to powder degradation?
Yes, I would. Actually, we've got some materials regarding that. I believe we've got some of the webinars actually. So if you look onto the webinar pages themselves, you should find some of our previous micromeritics webinars have dealt particularly with powder degradation. In that case, it was looking at reused powders. You can really apply the same kind of thought to sort of powders degrading through other means. I think really there's some complexity in this. So actually we can get back to you after the session on this. We can send you some further information because we've done quite a lot of work on this, but there's quite a lot to go through. And there's some sort of process-specific things. So, for example, if we're looking at binder jetting or if we're looking at SLS, we're going to have different recommendations for how you test that powder. But absolutely, yeah, we've done quite a lot of work on powders for additive manufacturing, both looking at metal powders and at polymers. So if it's okay, I'll get back to you after the session with some further details on that.
Thank you, Guy. With respect to testing, do you do this type of testing and consulting for a fee? A really practical question from one of the attendees.
So when it comes to just plain testing as a service, that depends a little bit on your location, whether or not we can do that contract testing. So in Europe at the moment, we don't have a great deal of capacity for that. I'm not sure it's the same in the US. They might have a little bit more capacity. When it comes to a consultative capacity, that's certainly something we can look into. What I would say is to drop us an email, or in fact, we'll get back to you after the session, and we can let you know what options are available. It's always a possibility. We just kind of have to work out what is the most useful thing for you, really.
We're almost out of time today, so this will be our final question for this session. Guy, does morphology have a significant impact on caking? And the real specific example that someone's asking about is lactose. Lactose monohydrate versus beta and hydrate, and batch-to-batch variability in this monohydrate and hydrate ratio. Have you seen cases or have you experienced with testing these materials?
Yeah, absolutely. So we've tested that kind of material quite a lot. We've got a lot of customers in the pharmaceutical industry, so lactose and that whole kind of family of excipients and whatnot. They're very commonly tested. And again, sort of when it comes to morphology, I get back to what I said earlier. Is yeah, absolutely. That morphology really affects the way that those particles are in contact with each other. So, even if you take something completely unreactive, just the sort of surface contact will have an effect just due to electrostatic forces and liquid bridging. So that is then exacerbated if you have any kind of chemical reaction as well. So whether we're talking about lactose or anything else, we would fully expect morphology to come into play. But yeah, I would say that those materials are some of the ones we're the most familiar with.
Thank you, Guy. That's all the questions we have time for today. If we haven't been able to get to your question, one of our application team will be in touch shortly. Guy, is there anything else you would like to mention?
Not really. I'd just like to say thank you to everyone for coming. And of course, if you have more sort of specific questions, or there's any sort of testing that you'd like to investigate that is perhaps a little bit different from this, please do feel free to get in touch anytime. We're always really happy to work with people on this kind of sort of method development and testing anything new. So feel free to get in touch anytime. Thanks all for coming.
Great. Thank you everyone for participating in today's webinar. If you have any feedback for us, we'd be grateful if you could complete the survey, which will be distributed in our follow-up email. We hope you found the session beneficial. Do not forget to check back for upcoming webinars on micromeritics.com/webinars. We hope to welcome you again soon.